So yeah, we'll be looking at fluids and almost kind of at an engineering standpoint. So in this first section, we're going to be investigating fluids alongside buoyant force. Okay, so we're going to define a fluid, distinguish a gas from a liquid, determine the magnitude of the buoyant force exerted on a floating object or submerged object, and explain why some objects float and some sink. All right. Yes, we're going to start off by just defining what a fluid is and looking at what makes a gas and a liquid different, which we should already know. But we also are going to show how they are similar and how we can utilize the similar properties for our benefit. You will have quite a few different what's it called? Formulas for this first section. Okay. And you'll also be sad to know that with this chapter, you have very little homework to go along with this one. This chapter actually goes very quickly. And we're looking at wrapping this chapter up by about the end of next week. Okay. There's not a lot in terms of what this book covers for fluid dynamics, but I always like to do this one because we do utilize these properties quite often. Anyway, also another statement that I want to make is that tomorrow you will have a quiz over this first section, but it is open up, open formula, open book. Yes. Formulas already. In fact, there's like 5 formulas, but they're all related together. Okay. So yeah, so open note, book, formula sheet. Obviously, it might be in your best interest to browse through the first section just to kind of get an idea about where information is located. Okay. But yeah, I think that's all you know to me. So a fluid is a non-solid state of matter which the atoms or molecules are free to move past each other. And this goes for something. You did a fingernail. What you did. So a fluid is consisting of both liquids and gases based off this definition. So since they can flow and change shape, they are all considered fluids. However, as we know from probably middle school, that liquids have a definite volume and gases do not. But I just want to have fun. Yes. But it's solid. The molecules cannot freely move past each other.
Oh no, moving past each other pretty good. But you put force into.
Are you chewing on it? Are you eating it? That's a non-Newtonian substance. So that's kind of its own deal. Yeah, Oobleck's interesting. I love watching experiments with Oobleck, like dropping anvils. Watch it. Yeah, I don't do the dropping of the anvils, Noah. But I watch this YouTube channel called How Ridiculous. Have you heard of that? Yeah. And they do some fun stuff, and they love Oobleck, and stuff they do is pretty funny.
Are those the dudes that take up the power?
Yeah, I love watching their stuff. Anyway, so just to demonstrate the fact that liquids and gases are different in terms of their volume, I need somebody who thinks they are. Again?
If no one else wants.
Yeah, no one else raised their hand. Come on up.
Well, no one else got a chance.
Yeah, they're all pretty excited. Come on up. All right. So we're gonna put this plunger at 40 milliliters. All I want you to do is place your finger there and use your other hand to compress that. Show the class. Show the class. Tell us how far you can compress it. Where does it end up? Start at 40. 11. Oh, you are strong. Okay, now let's do the same amount of liquid. Just to be like a doctor. There we go. All right. Watch you slip on that. Do the same thing if you want to get in the middle of everybody and see what happens.
Oh,
Come on, you say you're strong. Make sure you keep your thumb on there. Push! Disappointed. Yeah, ready? I mean, I got it to 25. All right, so again, similar properties, but not similar properties, okay? So we can harness their differences for our use. Anyway, this first section is talking about buoyant force, and it relates to density of objects and density of fluids, okay? The concentration of matter of an object is called mass density. That's not a new term to us at all. But it's measured in mass per unit of volume of a substance in terms of kilograms per meters cubed. Important units to know. So when we are talking about mass density in relation to buoyant force, we have mass density uses a variable of rho. RHO, okay? Where it's a little different than momentum, okay? Where it's just P, this is rho. So mass divided by volume, this is your first formula. Again, if you want to make sure you indicate that it is kilograms per meters cubed, that is what you should have. All right, so the buoyant force, in our case, is the upward force exerted on exerted by a liquid on an object immersed in or floating on that liquid, okay? Very similar to the normal force that we experience while we're on the ground. These buoyant forces are what keep objects afloat. And so how do large metal ships, they float like, what's that? Shipping ships, very good. Cargo ships. Or military ships. Okay, these are floating cities. Okay, aircraft carriers. How do they float? We're talking about tons and tons and tons of thick steel. Displacement. Okay, what is displacement? It moves the water.
yeah, like the weight of the ship is like.
Okay.
Also, like sinks, the farther it sinks.
Okay, so you said a few key things there. The weight of the ship displaces water, and the weight of the ship is dispersed by the size of the ship. So its mass is dispersed by its volume. Another thing you would need to know or think about is also, are these ships a solid piece of steel? No. They have a lot of caverns. They have a lot of open space. So a lot of that space within the ship itself is really just empty. You think about, yeah, we've got motors, we've got other stuff, we've got big computer systems, other systems in there as well. But again, having all that air that is essentially making up a good portion of the insides also allows for the mass to be reduced. And air being less dense than water also kind of gives it a little bit extra buoyancy, okay? So we have to displace whatever mass we are with appropriate volumes so that we can have that buoyant force interacting on a larger surface. And so this concept of buoyant force we saw in the video, studied heavily by Archimedes. Archimedes' principle states that describes that the magnitude of a buoyant force, and it says that any object completely or partially submerged in a fluid experiences an upward buoyant force equal in magnitude to the weight of the fluid displaced by the object. And so here is your next formula. So the buoyant force, the FB, is equal to the displaced fluid, FG. But FG, we can calculate simply by measuring the mass of water that's been displaced and multiply it by gravity. Now, what's happening with this ship on this next slide? Very good, Ty. But why, Ty?
Because the water.
Yes, that is the definition of thinking. But why? What's causing us to sink? Well, it might be difficult for you to see from there, but this raft has been punctured. Okay, it's an air-filled raft, much like a whitewater raft. It's been punctured. So as you see on the left, that the magnitude of the buoyant force, as well as the fluid that it's displacing, is allowing it to sit on top. But here we see that the buoyant force has shrunk. What do you think is happening? That's already been said. Its relative density is going up because why is the relative density going up? Yes, the volume of the ship itself is decreasing. As we are, again, letting air out, which again helps us with buoyancy, the overall volume of the ship, which is coming in contact with the fluid, is decreasing. The mass is staying the same, the volume is decreasing. So think about that mass density problem we saw a few slides ago. That density is going to become larger to where it's going to essentially overcome the buoyant force provided by the liquid. So, for a floating object, the buoyant force equals the object's weight. Again, you should be seeing now that if you go back, talk about FG of displaced fluids, when we talk about Archimedes' principle, and then when we get to a floating object, we talk about the density or the mass of the object. Okay, so we have to start denoting what thing we are talking about with our subscripts. Okay, so we are talking about the mass of the object times gravity. So when we have an object that's floating, we have what's called the apparent weight of submerged objects. Is going to depend on the density of the object, but also really the density of the liquid it's being submerged in. Okay, and so in order to calculate, now this is not a minus sign. Okay, this is not a minus sign, so pretend that's not there. Okay, no minus sign, it's just a dash, a bullet point. So again, essentially the mass of the object minus the buoyant force gives us our apparent weight. So with all of these kind of put together that we've seen thus far, we get this ratio. Okay, so for an object with density rho, submerged in a fluid of density rho f, the buoyant force, FB, obeys the following ratio. So this ratio we can use to help us find any of those four variables. So this is one of your last formulas right here. What's happening here? Other than a gentleman enjoying a nice read of the paper, which I knew that was coming. Hey, why is he floating? This is the Dead Sea. What about the salt?
Very salty.
Density of the water has changed because of the overabundance of salt that is dissolved in here, and it's hypersaline. Okay, it's not called supersaturated, but it's heavily saturated with salt. Okay, where the buoyant force, because of the density, is going to essentially increase, thereby keeping this individual afloat. Now, if you notice, how is he floating? Is he floating straight up and down, or is he kind of dispersing his body over a larger area? Yeah. So you still have to, configure yourself in a means to have a larger surface area, so you're increasing your volume in order to float like this. But yeah, it's a pretty neat thing. I don't know if I'd like to do it because I'd walk out of there looking like a grape right off the bat because, all that water, salt water especially, not necessarily good for the cells. But let's talk about how we can utilize buoyant force in, your everyday lives. And I know this scenario is pertinent to everybody in here. Okay? You are a bargain hunter looking for a crown. Pром's coming up. You don't want to buy the wrong crown. So you purchase this gold crown at a flea market. Exactly. I would. After she gets home, she hangs. They just hop right in and say it's a female. So yes, it's a female. After she gets home, she hangs the crown from a scale and finds it weighs 7.84 newtons. Sounds like something she should probably done while she was there. She then weighs the crown while it is immersed in water, and the scale reads 6.86 newtons. Question is, do we have a crown made of pure gold? You're saying no right off the bat. Why?
It seems like it right is.
Because you're a skeptical shopper. That's what you are. All right. So let's use some information that we have talked about thus far and go about solving this. So what do we know? We know that the object of the crown, or the mass of the object of the crown, is 7.84 newtons. Okay. The apparent weight when it is submerged is 6.86 newtons. And the density of our fluid, which in this case is just regular water, this can be found in a table on page 275. That's where this number is coming from. But 1 times 10 to the third kilograms per meters cubed. Okay? What we don't know is the actual density of the crown itself. So we have to take this information, along with what we've looked at in terms of our formulas, and try to decide how we go about solving this. And so, here's how we do it. Well, you can use this diagram here, but it's really not giving us any new information other than showing us the forces that are working here. So, plan of attack. What formulas can we use to help us? Our main formula that we need to use is that ratio formula. Okay? But we're missing some information. What from this equation are we missing from the information given from the question? We've got rho of the object, buoyant force. Okay? We don't have the buoyant force from we're trying to find density of the object. That's what our thing is, but we're missing a piece of information. That is the buoyant force. We're missing this FB here. Well, the other equation that we can use to help us find our buoyant force is right here. Okay, the equation for apparent weight. Well, if we know the quote-unquote force or mass of the crown, we are given the apparent weight in water. We can just simply rearrange this to solve for buoyant force, can't we? Once we have that, then we can move on to our next step, and that is using that ratio equation to help us solve for the density of our object. So, to calculate buoyant force, we take our our mass of the object, subtract our apparent weight, and we get our buoyant force of 0.98 newtons. Putting that number into our newly rearranged equation for the density of our object, we get that our crown has an overall mass density of 8 times 10 to the third kilograms per meter cubed. Now, that we know that, we can then compare it to what we should expect to see. And again, this is from that same table. This is what the table looks like on page 275. Gold has a mass density of 19.3 times 10 to the third kilograms per meter cubed. I think we've been hacked. You could calculate it, but using the method we did, we could still apply it the same way. So, but yeah, we are nowhere near the calculated density of gold. So she's been swindled. Take it back to the flea market. I'm sure they have a return policy. All right? All right. Questions on this? Now, the homework you're going to have tonight is a little different. Okay? A little different. You need to open up your books to page. Hold on. Page 288. On page 288, you have the Chapter 8 review. Up on the board, I have written the problems that you need to work on. You're going to put this directly on a separate piece of paper. Also, the first few questions are written responses. Make sure, as grown-up boys and girls, that they are actual sentences that follow, English narrative. Okay, so complete sentences. It don't have to be paragraph long. Single sentence typically is sufficient. So that's your homework. Again, do not forget your books, your notes, your formula sheets, or your calculators for tomorrow's quiz. These questions for homework tonight are very similar to the types you're going to see tomorrow. Yes. 288. 500. No. 588. 999. Yes.
Quiz tomorrow be completely
No.
now.
It is with a rare occasion that it's actually a book quiz.